So welcome everybody, and welcome to the actually the last lecture this semester. And what I'm going to do today is going to be a little bit shallow in the sense that I will cover ground which normally we use 2 to 3 lectures on, like autoencoders and the principal component analysis. But I just wanted to give you the kind of flair of it. And for those of you who are interested in using these methods, there are many code examples in the lecture notes. And this is also something which we can discuss during the lab sessions. So I will most likely talk about these topics for this lecture and parts of the next one. And then we are going to do a summary of what we have seen this semester here. So the topic today is a topic which we also, as I said, cover in other courses, and you will see links to that a little bit later. I did put up some videos on both autoencoders. The textbook by Goodfellow et al. With Benjo, who many of you probably heard two weeks ago, is in chapter 14. There's a pretty good discussion on autoencoders. And then in Rashka, this is only mentioned briefly in chapter 17, but there are also code examples there. And then there is a lot of literature and examples online. Now, when it comes to the lab sessions, this week is actually the last week of lab sessions, mainly because, I mean, next week and the week thereafter, many of you will probably be pretty busy with other exams. So we had openings last year, but there was only one who showed up. And then we decided that this week is the last one. And the other thing which I did, which I wanted to mention quickly a little bit about, is that we added some small things into project 1. So if you, no, sorry, project 3. And in project 3 here, we just added a small thing about the usage of large language models. We actually do want you to cite how you used it. And if you've been using that to write fractions of your report, we would actually like to see what ChatGPT or any of these large language models actually suggested. So please do that, how you actually, what you did in project 1. This is something which helps us in seeing if people have used these tools or not. Also, this is a course, or the topic of this course is a topic which you can basically find everything by calling any of these large language models. So it's a topic which is difficult to escape the usage of large language models. So we obviously want people to cite and document when you've used it and how you've used it. We encourage the usage of it, but obviously we want to see how people have used them. I hope that's okay. Else, the last set of exercises, which you have here, has a deadline. We announced it last Monday, and it has a deadline this Friday. And this is essentially just a set of questions about the different methods. Some of these are just true, false, and other ones are just some plain reasoning about what we have covered this semester. So that's the last weekly exercise. And I just remind you that every weekly set of exercises gives you a score of 1 point per exercise set. Also, there's been some problem with Canvas, which has been irritating us quite a lot. So when many of you register as a group, sometimes what happens is that there's only one who gets registered, which we see. So we are going to go through manually, as you probably saw from the email, we are going to go through manually all the weekly deliveries and just check that everybody has been accounted for. So I will send an email by the end of next week where I will ask you just to check whether all the weekly exercises you have handed in have been approved. Then we are planning to give feedback on project 2 by the end of this week. That's the kind of schedule which we have. So that means that you should have it roughly at least 15 days, 15, 17, 18 days before the deadline for project 3, which is December the 15th. Okay, any questions to practicalities? So I'm going to go back to the topic of autoencoders because I normally use that to catch two birds with a stone. And one of them is to link it with principal component analysis. And I'm going to give you a pretty sketchy view on what principal component analysis is. But the way you should think of autoencoders is as a way to reduce the dimensionality and find a representation which captures the basic features. So this is called the latent space. So you have an encoder which takes your data and then shrinks the dimensionality to some basic features, which you then use to reconstruct the data which you fed in. Autoencoders can also be seen as an unsupervised learning method. And this applies to principal component analysis as well. So that means you don't need to have labeled data when you use these methods. So many of the methods which you have looked at till now are methods where we have, when it comes to CNNs, recurrent neural networks, or neural networks, these are methods where we have had labeled data. Now, when you are solving a differential equation, if you are doing that in project 3, then you're using a neural network as an unsupervised method. Because the only thing you're doing then is to take the difference between the left-hand side and the right-hand side, and the network is finding the solution to the differential equation. And there is no need to have labeled data then. So even though when we have presented neural networks, we have said that this is a typical method which is used for supervised training. That means you have labeled data, X and Y. When you're solving a differential equation with neural networks, the neural network finds a solution for you. And the only thing which it needs then is the differential equation itself and an ansatz where you have in the boundary conditions and initial conditions. And the network is the ansatz. So even though the majority of the practical applications of neural networks is towards labeled data, you can also use it for unsupervised learning. So unsupervised learning is also something which we haven't covered that much in this course. So if you look at the autoencoders, this is a very powerful method for reducing the dimensionality. And as I said, I'm going to try to catch two birds with a stone by linking this with principal component analysis. So I'm going to take a detour where I show you what principal component analysis is and how that links with autoencoders when you make a specific approximation. So the picture which you saw last time is that of a input data which is fed in, so that is your X. You produce an output, so this encoder which you see here produces an output which we call H, and that represents your dimensionality reduction. So this could be a feed-forward neural network where you are just shrinking the dimensionality of the problem. You can do that. And then you have a latent feature, which is something you think are the essential features which represent the data the best possible way. So just to give you an example, suppose you have 1 million features, and perhaps only 100 of these are the important ones. That means that that specific thing you're trying to predict and label and characterize is something which you could get away with just 100 out of 1 million. So that means that to find these 100 features, which are the relevant ones, is something which we are always trying to target, because if you can shrink your data to a smaller dimensionality, then you can use that to reconstruct the full image, for instance. And this is what autoencoders are about. So let me quickly say something about this kind of link between the autoencoders and the principal component analysis. So in a typical autoencoder, what we have then is that we have a result, which is the result of the encoding part, which is this H. There can be a weight matrix, which links the input X with this latent degrees of freedom. And then you use that one to reconstruct the output, which is a decoder. And hopefully when you need a decoder, which you have trained as well, so you train both the encoder and the decoder, the simplest form could just be a linear dependence, which is the one we mentioned last time. And I'm going to show you how this comes through now. So in most typical architectures, the encoder and the decoder are neural networks, since they can be easily trained with existing software libraries like TensorFlow and PyTorch. And you will see in the examples below here that you can actually set up just a neural network where you have less and less nodes towards the latent space. And then there's a decoder part, which takes as input the output from the latent space and reconstructs your function here. And what you end up with then is an optimization problem where you're trying to find the difference between the input, x, and what is being outputted from your function. And then you minimize these parameters f and g. So a typical standard autoencoder is done via a standard feed-forward neural network. This is normally called a feed-forward autoencoder. And a typical feed-forward has an odd number of layers and is symmetrical with respect to the middle layer. So that means you could have a number of nodes here, n1 up to n2, and then you have the same number of nodes in the decoder part. So this is the encoder part. And you use this smaller and smaller number of nodes in a given layer to shrink your data into some essential features, which are then in the so-called latent space, or also the feature generating layer. And then you can train a network so that you can reconstruct it. So the things you would save then would obviously be the parameters of the network, but also the information about the latent space. And there's just a type of mirroring. So you would typically have the same nodes in the different layers for the encoder part and the decoder part. So I'm going to switch back to the whiteboard here and say a little bit about the type of links which we have with the linear approximation of an autoencoder and principal component analysis. So as I said, I want to describe both, and I want to show you the similarities. So an autoencoder is the same if you have a linear transformation, which I will show you now. If you have a linear transformation, it's the same as the simplest possible principal component analysis approach. And I will have to explain to you what the principal component analysis is about. So this is what I'm going to try to do today, and we'll see if I'm successful or not here. These activation functions, they are the standard ones, which you have used before. So there could be a relo, there could be a leaky relo, and the sigmoid function is also often used. And the cost-loss function is the mean squared error, if you're using that one. And then it could be a binary cross-entropy if you're dealing with a binary classification problem. And there's often something which is called the reconstruction error, where you are going to compare, this is actually the input which you're feeding in, and then the output. So the typical reconstruction error is given by the mean squared error. But let's now take a look at what this could mean. So let's go back to the image which we had here, and let's link this with principal component analysis. And I want to give you the detail of principal component analysis, because that will also allow us to remind ourselves about the singular value decomposition. So there are some elements of repetition as well. So let me see if I can give you this story in the span of 1.5 lecture. So let's see if we can do that. So if we look at the autoencoder, so what we have is, we just make a drawing again. Encoders. So basically you have an input layer, and we just write this with an Y here. Let me just call it Y. So this is our input layer. This feeds into an encoder. And this produces an output here, which goes into the latent space, and I call this for H. So this is the latent space. And the way you have to read this is as a dimensionality reduction. So we are looking after some few features which are the relevant ones. Now, this H then is then fed into a decoder part, which then produces an output Y tilde. And we want this y tilde to be as close as possible to the original y here. Now, this h, which you see here, when we have trained a model, so this is going to have some weights, w and v. So if we are now going to make a linear model, what we are going to assume then is that this h is now given by a w, and I'm skipping a bias, times y. So w is now a set of parameters which we are going to train. Then this y tilde is going to be given by, and this is normally called a function f of wy. And this y tilde is given by a function which depends on this v, which is a parameter, and h. And this is given by the v times y, no, sorry, h. So this is a linear model. It's linear in the parameters of the weight matrices w and v, okay? So now we are looking at the simplification. A neural network is not linear, we know that. So if we just had one layer, it could have been linear, but normally we have many layers, and then we get a complex non-linear behavior of the dependence on the different parameters. So you can make this more complicated, and you can think of the encoder and decoder as a feed-forward neural network with parameters to train, where you shrink the size of the number of nodes till you get to the latent space. And the hope then is that this latent space captures the essential degrees of freedom. So when you do this, what you have then is we can then write this y tilde as v times w times y. If we then want to optimize, so in the optimization problem, we want to optimize, for instance, the mean squared error. And in that case, we would have a function like this. And we've seen this many, many times before. And we have a y of I minus y of I tilde squared. And the optimization in this case, and this is roughly where we ended last time, this is us finding the optimal v and w. So we optimize or minimize with arguments v and w, and we optimize this function here. Y of I minus y of I tilde squared of I. And we know that if we look at that function, this function is nothing but, when we look at this linear approximation, linear prox, in that case, what we are optimizing is 1 over n. We have the sum over I, and then we have 1 minus, and then we have v times w times y of I here. And this is squared. So this is the function which we are going to optimize, but you should keep in mind that these autoencoders, AEs, now we had a linear behavior, so the AEs are in general not linear. Okay, so when I say not linear, it means that there's not a linear dependence here. Now, what I want to do now is to remind you of some things which we have seen before. So let's take a closer look at how we can link this with principal component analysis. So let's now put up a question, and let me see if people have been able to write down. So how do we link this AE, the linear one? And you can actually, we are going to show that this is actually the same link AE with the simplest, and this is normally linear, principal component analysis. So that will allow us now to catch these two famous birds with just one stone. we can present the principal component analysis, which is a very efficient tool to reduce the dimensionality of the problem. So in project number 3, if you actually want to use PCA, this is a powerful tool to reduce the problem if you have many, many features and you want to find out which are the important features. So as I said, if you have thousands and thousands of features, that means that your X matrix, the feature matrix, has thousands of columns and each represent a specific feature. You would like to understand whether we can limit the description and the training of a model to just some few ones. And this is what PCA offers. So autoencoders offer the same, and there is a one-to-one equivalence when we look at linear autoencoders and the simplest possible principal component analysis method. Okay, so this is roughly the setting. And let me try to show that gradually here. Now, if you look back at what we did in ordinary least squares, let me remind you of that. So in ordinary least squares, what we had is that with a design matrix, no, not design, can't write anymore here, design matrix, X, which now had n data points and p features. What we found then in the beginning of the semester is that this y tilde was given by x, and then we had 1 divided by x transpose times x of t times y. I guess I don't need to repeat how we arrived at that result, okay? Now, this is something which we relabeled as a matrix A. And this matrix A has a property that A squared is equal to A. So what we have then is that y tilde is now given by an idempotent matrix, which then functions as a projection matrix, where the projection is done in the basis of column vectors of the design matrix. So this is actually given by A squared times y, which is the same as A times y. Okay. Now, in this specific case, we have actually not performed a reduction of the problem at all. We are dealing with a full matrix A, but this matrix A projects down a specific set of vectors. If y tilde is equal to y, then A is just the identity matrix. Okay? And we discussed that when we set up the equations for ordinary least squares. That means that when we look at the mean squared error, and now I'm skipping the term 1 over n, but when we looked at the mean squared error, what we had then is that since this y minus y tilde is equal to 1 minus this A is a matrix times y, we can actually write this as 1 minus A squared times y. Now, if we now go back to the linear model which we had, what we have then is that this A squared is equal to V times W. So we are essentially now just comparing the mean squared error. And what we have is a function which now is the same, this A squared, which we had from ordinary least squares, now corresponds to this specific V times W, if we look at it mathematically here. So in this case, there is no reduction of dimension. And this term here is what we called a linear autoencoder. So AE for autoencoder here. Now let's also look back at some of the things which we did a little bit early in the semester. with the singular value decomposition. So let's remind ourselves of that, because that's going to be important now when we look at how we can implement the principal component analysis. So this is also a kind of a way to repeat what we have done. So we have the singular value decomposition, and you remember now that this X is given by a matrix of dimension n times p. P is a number of features. And then we could rewrite any matrix in terms of a unitary matrix U, a matrix which contains the singular value, times an orthogonal matrix or unitary matrix. So we are essentially dealing with orthogonal matrices. And we know that this one is equal to the identity. We have V times V transposed is equal to V transposed times V. That's the identity of dimension P times P. This is n times n. U is a matrix of dimension n times n. And V has dimension P times P. And the matrix D, which now contains the singular values, lambda 0 down to a lambda P minus 1, and then 0, has dimension n times P. So I'm just reminding you of some of the things which we saw way back in the beginning of the semester. And one of the things which we could do, so both the matrices U and V are invertible matrices. And one of the things which we found then is that when we now looked at the matrix X, we know that this matrix X, or when we rewrote Y tilde, we could then write it in terms of a sum from I equals 0. So we went through these exercises in the beginning of the semester. So now I'm just repeating them here. So this goes up to P minus 1. So if it went up to the final one, it would then be simply resulting in a unit matrix. So this is the kind of projection which we could do when we did the singular value decomposition. So what are we going to do now? So what we want to do now is to look at the connection between linear PCA and linear autoencoders. And these are mathematically equivalent. Now, in order to do so, we need to look at a quantity which is called the covariance. And we discussed that sometimes in the beginning of the semester. So we need, and I'm going to set down the recipe for the PCA, need the covariance. Covariance in order to set up the principal component analysis. So principal component analysis is a way to reduce the dimensionality of a problem. So let's now look at the covariance. So if we now take the design matrix which we had, X, we know that this is something which we can write out in terms of different vectors. So these vectors are not necessarily orthogonal. And then we have up to X of P minus 1. And these are the vectors which then contain the data sets which we have. And if we now look back, one of these single vectors, X of I, transposed, would then be given by X0 of I, X1 of I, and all the way up to Xn minus 1 of I. So this is how we defined the design matrix in the very beginning of the semester. And this is the way it's going to look like if we are going to feed that in as our data set, irrespective of type of problem. So the features could be, let's say, the number of rooms, the number of bathrooms, the size of a house, etc. Or it could be a particular problem like if you're dealing with some medical research, it could be properties connected with your heart, for instance, if you're studying cardiac disease, etc., etc. So these are features which you would have. And then in that case, the medical data set, the N's would then be the number of patients which you have surveyed for specific properties. Okay, so the covariance, and I need to define that for you. So suppose now that the covariance itself of one of these vectors. So let's take now an example, and I'm going to write this x0 and x1. And suppose now that the matrix is equal to, so this is the input data. So I have x00, x10, x20, and this is just x01. So these are just data, and 21. And we are going to look at a specific example a little bit later. And we would typically write this as a vector x0 and as a vector x1 here. Then what is pretty common to do is actually to rewrite. So if you look at this x of ki, it's common to rewrite them into an x of ki tilde, which is given by xki minus the mean value. Of a given column. This is what you do when you scale your data, right? So it's pretty common, you scale your data by subtracting the mean value for every column. So that gives us this x tilde, and then of plain laziness, I'm now going to let xki tilde, because I don't want to carry a tilde, to just be xki again. So this is just a notation which I'm going to implement. So these xki's are just going to be the values with a subtracted mean value. And this is our scaling of the data. It's a pretty common thing. So this is our standard scaling of data. So I'm using this to repeat some elements as well. Our standard scaling, you could divide with the standard deviation as well. So the covariance, how is that defined? So the covariance is defined for two vectors, xi and xj. This is defined as 1 over n, and this is a sum over k, and then I have this xki multiplied with x. So this has a sum over k, and this has a kj here. And these are these scaled numbers, okay? I'm taking away the tilde here. So if you now take this x0 and x1, what you will find then is as follows. So let's just write it out. Is that okay? Can I just move? So if I take the example which I have here, this covariance of x0, x1, the simple example, this is going to be 1 over 3, and then I have a sum up to 3 elements, xk0 times xk1. This is a k here, and that is equal to 1 over 3 when I just write everything out, x00, x01 plus x10. So these are all elements of the design matrix. And what it measures is the degree of correlations between two features. So you remember that in the very beginning of the semester, we calculated the correlation matrix for a data set. And when we then scaled it by the standard deviation, then on the diagonal of that matrix, we had just ones. Else, this is going to be the variance. And with that, we could say something about the degree of correlations between different features. So if the degree of correlations between some features are close to 0, then it could happen that we could skip some of them. So what we have then, if you look more closely at this, this is the same as 1/3 multiplied. So we have x00 vector, x10, x20 multiplied with x01, x11, x21. And this is nothing but 1 over 3 of x transposed times x0 times x1. So where are we going now? Where we are going now is as follows. So let's take and redefine things a little bit. So if I think of a matrix, if I take the covariance of the design matrix X, so what I wrote here was the covariance of these vectors, but I can now set up the covariance of the matrix X. This is actually the same as 1 over n of the matrix X transpose times X. And this matrix is something we have seen before. That's the one we have inverted when we do ordinary least squares. So this is one of the nice things with ordinary least squares, which we didn't discuss thoroughly in the beginning of the semester. So the covariance matrix is actually the same as the matrix we are inverting in ordinary least squares. And we have already done the mathematics of this matrix. And I'm going to remind you of some of the mathematical properties when it comes to its eigenvalues. So if you look at our example where we had only 2 vectors, so if you look back at this example here, where we now have a matrix which looks like this, if we do the mathematics here, then we will see that the covariance of this matrix X, when I write it in this more compact way, is 1 over n. And then what I have here is x0 transpose times x. And here I have x0 transpose times x1. Here I have x1, they actually symmetric transpose. So it's going to be a symmetric matrix. And it's going to be a square matrix. And then I have x1 transpose times x1. Like that. And a quantity like this one, 1 over n of x transpose, x0 transpose times x0, it's actually 1 divided by n of k of xk squared of 0. So in principle, this is actually given by the tildes. So this is 1 over n, and then I have k, and then I have xk0 minus x0, and this is squared. So this quantity has a name. Does anyone remember that? If you think of statistics, yeah, that's the variance. This is the variance. So variance, this is equal to the variance. And we normally wrote that as a sigma squared. So this would be sigma 0 squared. So that means that I can actually rewrite this covariance matrix of the matrix X is equal to a sigma 0 squared. There's a covariance of x0, x1, and then I have a covariance of x1, x0, and then I have the variance of sigma 1. Now, what is common to do is actually to not set up the covariance matrix, but the correlation matrix, because the covariance can be a large number. And the variance can be a large number. So if I divide by the variance or the variance along the diagonals, then I can define the correlation matrix by simply dividing by the variances. And the correlation matrix has matrix elements. This is normally the quantity you would see. So we would write this as a correlation between 2 vectors, xi and xj. These are the column vectors of your design matrix. And that is simply the covariance of the 2 vectors of xj divided by the variance of xi and the variance of xj. So you can do that, and then you would simply have 1s along the diagonals. and a finite number or small number along the non-diagonal. Now, let's now take a closer look at this. So the x's are stochastic variables, and you can assume that they are independent and if these x's, if they are stochastic variables and they are independent and identically distributed, then this quantity is exactly equal to 0. So that's nice. Now, normally you cannot assume that. So if I want to calculate the eigenvalues of that matrix, what I would typically do then is to perform a transformation. So the transformation, so let us assume now that the x's are given by stochastic variables. So if I want to have the eigenvalues, so if I now look at this covariance of x, this is nothing but the expectation value of this quantity x transpose times x, which is the same as 1 divided by n times x transpose times x. Now, if I set up a matrix S, which is a orthogonal matrix, and I want to find the eigenvalues of that matrix, we know that what I would have then would be an S multiplied with 1 over n times x transpose times x multiplied with S transpose. That's a typical way I would then turn this into a diagonal matrix. And that matrix, since these are non-stochastic quantities, so this is non-stochastic, the x's can be stochastic, then since this is an expectation value, what I'm having then is S multiplied with the expectation value of x transpose times x multiplied with this S transpose. That gives me a new matrix, which is diagonal. So that gives me a matrix, which I'm simply going to call the covariance of y, which is then the same as 1 over n. And then I have a matrix yt or yt here. And this is the same as the diagonal sigma 0. I put a sigma 0 squared tilde here because it's I have diagonalized a matrix, and I have a sigma p minus 1 squared. So this is the variance. So when I perform such a transformation, I can then find the eigenvectors, and that is the covariance matrix for the variable y, which is a new design matrix, which is now diagonal. And what I have there is just simply the variances. Now, one thing I wanted to remind you of is, before we take a small break, is back to the SVD. Because we can find these eigenvalues quickly. So you remember now that x is given by a matrix U times this matrix diagonal times a matrix V of t, which is orthogonal. So that means that this quantity which we had, 1 over n of x transpose times x, is something which I can write out as 1 over n. And then I have V, I have this diagonal matrix dt, I have my matrix U of t times U, and then I have the matrix D times the vector V of t. And that is the same as 1 over n. We know that this one is just the identity matrix. And this is an identity matrix. When I multiply it with D of t transpose times D, this becomes a matrix which is just V times this D of t times D of V of t. And this has now dimension P times P. And I can write it, and this is what we did early in the semester, like D squared times V of t. Now, what I know is that these elements which you have here, these are the singular values of a singular value decomposition. So what I can do now is actually to get these eigenvalues if I do a singular value decomposition. Because I know then, if you now look at this quantity which we have here, if I take now my matrix, so this is the same as 1 over n of x transpose times x. Let's just get rid of this guy. Let's do that. And then what we get then is that we have x transpose times x is the same as v times this matrix d squared, v of transpose vt. I multiply from the left with v, now from the right. What I get then is x transpose times x times v is equal to v times d squared. And then v is now just one of these eigenvectors, v0, all the way up to vp minus 1. That means that x transpose times x has the v's as eigenvectors and the sigma i's as eigenvalues. So that means that the matrix, which I have now, this matrix x transpose times x, it has as eigenvalues the singular values, and these are the variances. So in this case, what I have now is that the sigmas, the singular values, sigma 0 squared are sigma 0, sorry, sigma I are, if I now divide with 1 over n, are the variances of the covariance matrix. So the singular values, which are then the eigenvalues, are then the covariances. That means also that these eigenvalues, which I have, sigma 0 squared, is assumed to be larger than sigma 1 squared, larger than sigma 2 squared, etc., and larger up to sigma p minus 1 squared. And this is normally larger or equal than 0. So actually larger than 0. So I just went a little bit over time. So where's the principal component analysis? Now, the principal component analysis means now, since every row here represents a feature, we now keep only the largest eigenvalues so that the sum of all the variances from I equals 0 up to p truncated. So in principle, this is the total variance. Total variance. What we do when we do the principal value decomposition is the following. We actually make a truncation where we have I equals 0 up to, since these eigenvalues are ordered in as a descending series, we keep them up to value d. And this is smaller or equal to a truncation value. So this could be, let's say, 95%. Or let's just put a specific value here, which we just call for a cutoff. And let's just call this a uppercase lambda. So this uppercase lambda could be us keeping 95% of the total variance. That means that those eigenvalues, which are the singular values, which are also the same as the variances, they are then truncated, and we keep only variances up to a specific value. So you could now think that 95% is represented by the 10 features only. And if you have 1,000 features, you're leaving out 990 features. So you keep only those which have the largest singular values, which are the same as the largest variances. So that's a way to truncate the effective degrees of freedom by looking at the correlation matrix. So the correlation matrix tells you about the correlations between data sets. So if you have large correlations, you want to keep that feature. If you have essentially zero correlation, you just skip that feature. And this is reflected in you truncating along the line of the values of the singular values. If you sum them up here, singular value squared, that corresponds to the total variance. If you truncate it, you keep only specific features. So this is principal component analysis. And if you have 1,000 features and you keep, let's say, those which represent 95% of the total variance, and these are 10 features in total, then the model you want to fit contains only 10 features. And that is a considerable reduction of the dimensionality. So this is how principal component analysis actually performs a dimensionality reduction. And since everything here is linear in the transformation, because what we have is a transformation in terms of the singular value decomposition, then this gives us something which is exactly the same as this linear autoencoder, which then can be seen as a similarity truncation here. So let's take a small break, and then we pick it up again, and then we're going to use some 20 minutes of the next lecture to finalize this PCA discussion, and then we are going to try to wrap up what we've gone through the semester. I know this is rushing a little bit. I told you that I will do that today, but there is much more details into the lecture notes as well. So let's take. So what I wanted to say is that the principal component analysis is a way to reduce the dimensionality by looking at the singular values. So if we can take the the covariance matrix, find the eigenvalues, then we can make a truncation and say that it's only the 10 largest eigenvalues, which are the same as the singular values, which are identical with the variance. So if we then sum up the total variance, we can make a truncation. And this is the standard way the principal component analysis is used. Now, how does this connect with an autoencoder where we have a linear transformation? So let's just go back to what we saw before the break. So when we now looked at the error which we want to study, we had a 1 over n. And if we use the mean squared error as a kind of reconstruction error, what we had then when we had a linear case was 1 minus, and then we had this vector W and matrix V and W, which then define our transformations, and this is squared. So what it means is that our model Y tilde is given by this V times W times Y. Now, when we then have performed a principal component analysis, or the analysis which we did previously, so in an SVD analysis, which is the basis of PCA, that's one of the ways of looking at it. What we have is that this Y tilde is then formally given by the sum from I equals 0 up to P minus 1 of UI, the vectors of the matrix U. So this matrix U is then given by a set of orthogonal vectors, U1 up to U of P minus 1. And then we have a U of I transposed multiplied with Y. And what you see now is that mathematically, this is what we get from the PCA analysis, or based on the SVD. And this expression here should then be the same as this expression here, when we now are setting up the mathematically the equivalence. Now, if we truncate in P here, and we keep those eigenvectors, or actually those eigenstates, which are then the variances, which are the largest ones. We could then make a truncation here, as we did here, up to a given value. So if we do that, if we truncate this sum, then we are doing a dimensionality reduction. We are reducing the dimensionality of the system. So if you have 1,000 orthogonal vectors, and you keep only the 10 first, which corresponds to the largest eigenvalues, which are the largest variances for the covariance matrix, then that is a truncation. We reduce the dimensionality of the system. So a principal component analysis is a way to reduce the dimensionality of a system. So let's look at the recipe. So we are going to look at the way you typically implement the principal component analysis. And an autoencoder, if you have this linear dependence, like the one we put up here, acts like a truncation algorithm for the effective degrees of freedom. So keep in mind now that this matrix U is set up according, so the eigenvectors are actually more eigenvectors here of that matrix. This actually continues up to U of n minus 1, but we keep only those which have a singular value different from 0. And that gives us a projection of the data based on this. If we were to keep all, this would just give us a identity matrix, and then y tilde would be equal to y. The same as if this case here, if v times w was given by the identity matrix, then y tilde would be the same as y. So the connection between an autoencoder and the principal component analysis is then given by this equation here and the equation you see here in case we have a linear transformation. An autoencoder, however, does not have, in general, a linear transformation. It's actually given often by a neural network. It can be a convolution neural network, etc., etc. So the principal component analysis, if we now go back to the Jupyter notebook and take a look at it, we can then try to build up some insights about the principal component analysis by looking at a simple example. So let's just increase the font a little bit. So the algorithm is just as follows. So we would set up the design matrix for principal component analysis. We center the data by subtracting the mean value for each column, as we discussed before. We then compute the covariance, alternative the correlation matrix, and then we find the eigenpairs with eigenvalues, lambdas, etc., and eigenvectors. And then you order the eigenvalues and the eigenvectors accordingly in order of decreasing eigenvalues. And keep only those L eigenvalues that are larger than a selected threshold value. And then you discard the P minus L features, since we expect small variations in the data then. So let's try to build some intuition here. So I'm just giving you an example. So we are taking two vectors. And these vectors, the way I'm going to do that, so this is the covariance matrix of two vectors where each has 10,000 points. These are the mean values. So these are Gaussian random numbers, and I picked 10,000. And remember now that since I have two mean values of these 10,000, these are just Gaussians. This is now my covariance matrix. And then I can just set it up here. You can see now I have 10,000 points. I have a multivariate normal distribution, which then takes this mean value and this covariance. So if I run that one, this is the first step. Now I perform the subtraction of the mean values. And you would, if you use pandas, this is just the way you would scale the data. You have the center data here. And then if I now look at my center data, this is what I would have. Nothing particular here. I'm not getting exactly 4. I'm not getting exactly 2. So this is my covariance matrix. If we go back here, 4, 2, 2, just an example I chose, then you see you don't get exactly 4 and 2 because we have only 10,000 data points. If I were to take 100,000, I would be getting closer. Now, if I make a plot now, so what I'm going to plot, these are all my data points. And you see now that I have 2 vectors, and this is how these 2 vectors distribute. Now, what you see here is that I cannot make a truncation here where I say that I skip one of the vectors, because they look pretty well correlated. Now, one thing I could do now is the following. If I go back to the problem which we had here, now sometimes this disappears actually. This is something which has been irritating with the Jupyter notebooks lately, that when I don't know why that one happens. So let's just scroll down again. And now I'm going to set up a covariance matrix where I instead have 0.1, and I do 0.1 along here. And I also put this one to be a pretty small value, 0.1. So what we're going to see then is something which is slightly different. So let's just rerun everything here. And now you see something like this. So what I'm doing now is simply to plot the 2 eigenvectors. Now, in this case, the big scatter, because I have a variance which is 4, the big scatter is along the x-axis. And you see I have a very small scatter along the y-axis. So what I could say now is that most of my values are along the x-axis. That's where I have the big scatter. And then I could simply say, okay, now I just leave out one of these as degrees of freedom. And that means the degrees of freedom are along the y-axis, because it's along the x-axis where I have the biggest scatter. This is essentially what the principal component analysis is doing. It picks the largest eigenvalues. It means for this simple case here that we are now omitting those cases where the variance is small. So when you now look at this simpler case here, where I changed from 4 and 2 as a variance, you see now that this is now the variance which I'm looking at. So it's a 4 here, and it's a 0.1 here. When I diagonalize this one, this is going to have a eigenvalue, which is going to be at least 1 order of magnitude larger than the eigenvalue here. So I could just use that to leave out those degrees of freedom. And that's what the principal component analysis is doing. And you can see that very clearly here, where you now have a very small variance, or you also have a small covariance here. So there's little correlation between the data sets. If I were to put this one even smaller, if we just repeat this exercise, and even smaller, and then I could have an even smaller here, and then you would see that this problem then gets reinforced, and then we can really forget about one of the degrees of freedom. And then you see now that when you look at this one, it becomes even flatter here. So if you then wanted to reduce the dimensionality of the problem, you could simply say that I don't care about the degrees of freedom represented by the y-axis. So when you diagonalize, keep in mind then that when you're diagonalizing that matrix, then these are vectors which are orthogonal to each other. And I'm leaving out, in this case, one of the vectors which is orthogonal to the one which I think is the most important component. So if you do this with 100 times 100 matrix, and you pick the 10 lowest under the 10 largest variances, the 10 largest eigenvectors, you could leave out the remaining 90 degrees of freedom. And then you could simply then say that, okay, I now make a fit of a model with 10 degrees of freedom only. And that you see is something which simplifies the whole analysis. Now, with a singular value decomposition, you can always reconstruct what you didn't have. Okay? So just think of this, because when I have the eigenvectors, I can always project down the dimensionality and make a fit. But then, since I know the eigenvectors of the singular value transformation, I can reconstruct the input which I have. So if we then go back to that image of the autoencoders, which we had in the beginning, this one, you can then think of an autoencoder if we have this linear model, which we discussed, which is normally not the case. You could then have a way to reduce the dimensionality. This is your latent feature. With a singular value decomposition, you know the singular vectors, and you can always reconstruct with a decoder by recalling your vectors and then reconstruct the full input which you had. With the autoencoders, what you're doing then is that you're training a neural networks which finds an effective degrees of freedom, an effective space, a latent feature, and then the decoder is trained so that the error which you get, and that is the reconstruction error, which in that case could be, let me see where did I put it, it could be the mean square error, or it could be the cross entropy, that these reconstruction errors are as small as possible in the training. So it's a way to find a smaller space without having to go through, let's say, a singular value decomposition. A singular value decomposition is something which then has to be done by standard linear algebra methods. And if you have thousands and thousands or millions of features, then it becomes almost impossible to perform a singular value decomposition. And that's why autoencoders are so popular when you have many, many, many degrees of freedom. So for those of you who in project number 3 would like to use autoencoders and PCA, this is a perfect match of data sets where you want to reduce the dimensionality of the problem and where you often have an unsupervised problem. So PCA is often used as a way to reduce the dimensionality when you don't have labeled data. Now, in the Jupyter notebook here, if you scroll down, what you will find is also a set of examples. So there's a little bit more about the PCA analysis. There's also a analysis, and you can see now if you calculate the eigenvectors and the eigenvalues for the last case, you will see that the eigenvalues are of this case is actually 100 orders of magnitude, 100 factor of 2 orders of magnitude smaller. Now you can actually use the we're going to skip this. There are some references, but if you want to use software like scikit-learn, you have the possibility now to use what's called scikit-learn decomposition, import PCA, and then you simply specify how many components you want to keep of a full data set. So if you now want to keep only 2 components, and suppose you have 1,000 features, it then keeps only the 2 features which have the largest singular values. And this is what PCA actually does. So in the slides here, you will find a comparison between the usage of the standard PCA, which you find in scikit-learn, and also the my own homemade case, which is the one you will see here. And you will see that the eigenvectors are essentially just the same. That's a useful test, actually. I'm just inviting you to take a look at these codes if you want to use this. There are different types of PCA. There is one thing which is called kernel PCA, which we discussed a little bit in the beginning of the semester, what that means. I'm just going to illustrate that by an example. So the kernel trick is something which is widely used in machine learning. So let me just quickly illustrate that before we jump into a summary of the semester. And this is something which is useful to do and to keep in mind as a possibility. So suppose now that you have a data set for classification. And we discussed this actually some time ago back during the lectures. So we have some Y, we have some X, and then we have some data sets where we want to distinguish between circles and crosses. So these are the crosses, at least my attempt of making crosses. Now you see now that in this particular case, if you look at the data as they are, it's difficult to find a plane which separates the crosses and the circles. So you could think of you making a, not a classification problem, but you could think of a regression problem where you're looking after a plane which separates these two, but then you see if this is my plane, I cannot distinguish these two. Now, one thing which is common then is actually to transform the data by a kernel trick. And the kernel trick means that I would transform these values by squaring them. So if I square them, so let's do that. And here I have 1 and -1. If I square the values, these will still stay below 1, but then the crosses will become larger. And then you see that it is actually pretty straightforward to find a line which separates the two. And in that specific case, what you have then is a kernel trick where you have simply squared the values. Actually, this should be above here, a little bit above. But you have squared the values. And what that means is that you can find specific types of kernels where you transform your data set. Now, in the literature, you will find many different ways of doing it. And when your data is much more complex, it lives in many dimensions, then it's very difficult to visualize a simple way to transform the data. So what people end up doing then is to try different transformations and see the one which gives the best fit. So you can have an exponential with Gaussians, you can have x squared, y squared, etc. And these are just kernel transformations. That's a typical trick which is being used in the literature, which we haven't discussed that much this semester. Okay, so let's go back to the Jupyter notebook. Now, in the slides here, you will also find examples of usage of autoencoders, one with TensorFlow, and I invite you to take a look at it. We will not discuss this in that much detail here now. You will find with TensorFlow a case where you can just set up a standard neural network with different activation functions. We have the encoder and decoder part. There is, if you scroll down, you can use convolutional layers instead of dense layers. So you can have, instead of having a standard feed-forward neural network, you can have a convolutional decoder and encoder. There is another example here where you can have recurrent autoencoders, etc., etc. And if you scroll down, you will also find an example with PyTorch as well. And this is the one which follows here for the data set which you have seen again and again and again, which is the MNIST data. So if you're interested in making a comparison between principal component analysis and autoencoders, and I know that some of you actually want to use that, it's a little bit more advanced topic, but that is something which would fall within the topics which we have covered this semester. Although for this topic, I have been a little bit, shallow, in the sense that I haven't given you all the details about autoencoders. So I hope you can forgive me for that, but we didn't have enough space here. But these are methods which are widely popular, and we discussed them also in more advanced courses in the spring. And that brings me to a kind of summary of many of the things which we have done this semester. And let me just bring that up. They're just coding examples. And I'm going to take this. I actually love this figure here. I hope you can see that. So as you probably noticed, there's no final exam here. And This is actually the way I often felt before exam. Procrastination is one of my favorite hobbies. And 2 days before the exam is like that. And then after the exam, it's like this. How many of you have been in that situation? I think that's pretty familiar, right? So the nice benefit with having a project-based way of teaching is that we avoid that situation. And hopefully this has given you more insights into what the method's actually doing, especially when you have coded the neural networks. Because a neural network, as you saw now with autoencoders, with recurrent neural networks, with CNNs, is actually the basic building block. It's an essential Lego building block in everything which we do in deep learning. And you will encounter them in transformers, you will encounter them in reinforcement learning, etc., etc. So having an understanding of what the methods are doing, and you having coded a deep learning method like a neural network, I think that's something which is essential. So we have looked at statistical analysis and optimization of data. The optimization part is actually very important. And project one was actually about that. And then you have reused that one in neural networks. And we have looked at machine learning methods. So when it comes to analysis, statistical analysis, we have looked at some basic concepts like variance, covariance, correlation functions and errors. We haven't been so keen on these things this year, but we have talked about central elements from linear algebra like matrix inversion and singular value decomposition. Gradient methods for data optimization have been central methods. We have used cross-validation and bootstrapping. And then we have looked at practical optimization using singular value decomposition and least squares for parameterizing data. Actually, we did discuss this now, but we haven't gone that thoroughly through it. We have done ordinary least squares, ridge, lasso, logistic regression, neural networks, convolutional neural networks, recurrent ones, autoencoders, and PCA. What we haven't discussed are decision trees, ensemble methods like random forest and gradient boosting. And we haven't looked at much in depth on support vector machines and kernel methods. So in the beginning of the semester, I actually made this list on learning outcomes. So the thing I always invite you to do when the semester is over, actually take a look at the ideal here. And we have been looking at some central algorithms. And the question now is whether you feel that this course has actually deepened your understanding of some of these topics. I'm not going to dwell too much on it, but I want you to actually think a little bit whether the things we set out to do, whether this have been achieved or not. So take a look at these, and then this is something we can discuss during the lab sessions, and you can give me feedback and all the other TAs which we have at the lab. There's a perspective. Clearly, if you look at the machine learning, this is a rapidly developing field. So one thing which is now going to play a big and bigger role are actually large language models. And I guess everybody has some kind of variant of deep research on ChatGPT or Claude or whatever. And these are tools which I really recommend using. Now, one thing you will see, and you have to be careful with, like when you're writing the references for the report, I don't know if you checked your references. If you ask ChatGPT or any of these large language models to set up a reference list, sometimes you can risk that it just comes out with garbage. So somehow when you set up references, it can mix authors, it can give you wrong references, etc. So this is something which is important to check. On the other hand, when you look at the topics we have covered this semester, this is actually one of the fields where there's so much data which has been used to train the models. So if you ask it to write a decent introduction about, let's say, ordinary least squares or neural networks, it will actually do that. But you should obviously try to write your own first. Go through the process where you look at the literature and see if you can come up with meaningful wordings, because it's you at the end who has to gauge whether the quality of what comes out is correct or not. So I can just give you an example, because I teach a course on in parallel with this one on many body physics, which is just quantum mechanics applied to systems of many interacting particles. And for the midterms, many of the people attending the course have tried to use ChatGPT and ask ChatGPT or Claude or any of the other ones for advice. And what comes out, because there's so little training from this field and there's so much niche knowledge, that what comes out is often just plain garbage. It doesn't make sense. So that means that at the end, it's you. Even if there is so much which has been used in the training, in machine learning and AI, it's still you who has to gauge whether what comes out is reasonable or not. Especially if you use it to write an analysis of the data, because sometimes it can hallucinate and just write very odd things. And we see that when we read the reports. And that's why we want you to also list how you use these resources. We think these are very useful resources to use, and they can do a good job, but you have to assess whether this is good or not. That means that you need a deeper insight. And hopefully this is what this course has given you, a deeper insight about the methods, so that you can actually assess whether what comes out from a tool like that one is reasonable or not. In a certain sense, what you're doing is what I did when I started to write my first scientific stuff, because I would read papers from other people, I would read books, and sometimes I just adopted paragraphs. Well, I didn't adopt them, I just rewrote them, but I use that as inspiration, because I mean, most of us have never written a scientific paper in the very beginning. So it's a very useful tool, but it has to be used with care. So the large language models are also going to play a much, much bigger role, because they're going to save you time. So there are many boring operations when you write code. If you have the ideas and the insights about problems you want to attack, this can save you time in developing boring parts of the code. But then you have to be sure that it does the correct things. So I use it often. I have ideas on what I want to research. And then sometimes it can save me a week of coding. But I have been coding for 40, 50 years almost. So I know where the bottlenecks are, et cetera, et cetera. Now, one thing, so this just contains a long, long list of things. I invite you to take a look at it yourself. Typically, if you now look at the starting a machine learning project, you have to first identify whether you want to do a classification or regression. Consider your data carefully, whether you need to scale, if you need to scale, and how you should scale. You should choose a simple model that fits 1 and 2. That's often the best way of starting. And then you consider your data carefully again, and think of data representation more carefully, and based on the results, feedback loop to earliest possible point. So you can keep enlarging the model. So to link this with a principal component analysis or an autoencoder, the way you could think of it, suppose now you have a design matrix with 1,000 features, and you start making a reduction, and you say you keep only the 10 features which have the largest eigenvalues or the largest variances. Then you fit a model. Suppose that gives you a mean squared error of 0.1. Then you increase from 10 to 20 features. And if that gives you a mean squared error which is smaller, you would say, okay, I need probably to keep 20 features instead of 10 out of the 1,000. And then you could increase till you reach a mean squared error which you would accept. Then this is the kind of way you would continue if you're using something like a principal component analysis. It's also principal component analysis is a nice way to point out which features are the most essential one, because that will allow you to make an explainable model. And you would say that for the housing prices, the most likely feature is the size of the house, the number of rooms, the number of bathrooms, just to give you an example. Then you choose algorithm, whether it's supervised, you start with the simplest model that fits your problem. and then you start with minimal processing of data. Then you have to shuffle your data, mean center your data, normalize the variance, Y, decorrelate data, etc., etc. These are things which we have discussed, which activation function should set all weights to 0. That's a terrible idea. Set all weights to random values. Normally you would have small random values. Then the number of hyperparameters, the type of methods, stochastic gradient descent plus momentum, root mean square propagation, Adam, etc., etc. And then which regularization and hyperparameters are useful. Then you do resampling, and the most common one is actually cross-validation. Bootstrap is another one we've been discussing. So these are all elements which we have been discussing in this semester, which enter the actual, how to say, pipeline when you are developing a model to fit some data. And at the end, it's you who has to decide which type of algorithm, which type of method, which type of architecture is the best one at the end. So hopefully we have given you the tools to see that. And then we have lots of courses which actually bring in more advanced models and algorithms. So I just wanted to list some of them in case you're interested. So we have one on advanced machine learning and data analysis. So this focuses on generative methods like Boltzmann machines, variational autoencoders, diffusion models, reinforcement learning. We have this course, which many of you probably have taken if you have a bachelor degree from computer science, informatics. The same with this one, and also the one on natural language processing. This is one which runs in parallel with this course, and many of you have actually taken this one in parallel. That gives you a kind of statistical analysis point of view, but it focuses mainly on the non-deep learning methods like random forests, gradient boosting, etc. And as you can see here, there are many, many other courses. This runs in the spring, and it's a very popular one, machine learning. This is for image analysis. And this focuses on convolutional neural networks, recurrent neural networks, also transformers, which are covered by other courses as well. I don't think it covers reinforcement learning. So we have had a big focus on the basics here. It means that many of the really interesting research methods like transformers, reinforcement learning, generative methods are things which are typically covered in other courses. But this course serves as a kind of entry point so that you can gauge whether you find this interesting or not to continue. And as you can see, there are many, many other topics here at the university. There are also courses in statistics, which are actually very interesting. This runs, unfortunately, during the spring semester. So the applied Bayesian machine learning is a topic which is very, very hot. So the reason why I mentioned that is that if you think of what we have been doing here, what we have been doing is to take in data, we fit a model, which we use to make predictions. Now, if you look at what we discussed today with the covariance matrix, you can find correlations in the data set. This is very useful because then you can tell people that these and these features are correlated and these are not correlated. Maybe we can skip some of them because they are less important. So we have mainly focused on fitting data. And that means that we have had the focus on prediction and correlations. Now, when you move to generative models, where you actually produce a probability distribution, you can predict, you can produce new data, which you use to unknown cases. You can find correlations when you have a probability distribution, but you can also test causality. So when you have a probability distribution, you can say something about what is the likelihood of A given B. Also, when you have a probability distribution, you can find the errors. in the parameters. This is something which we normally don't get with what we have done in this course, essentially because we have stayed with what in statistics is called a standard interference model. No, not interference. What's his name again? Oh, the name, I've forgotten the name. But we have the Bayesian approach, and then we have the standard where you infer from the data a model which allows you to make predictions. So generative models, which are discussed in more advanced courses like this Physics 5429 in the spring semester, they allow you to generate a probability distribution. And this is normally what is used in, let's say, these programs like large language models, where you produce new images of horses, etc., or cats or whatever, but also in Bayesian statistics. So Bayesian statistics is based on Bayes' theorem, which is like Pythagoras in statistics. And it's a fundamental theorem, and it allows you to train a probability distribution, given some prerequisites and ansatz. So I would say that if you think of the future, there's so much which is going on. And I would say, like, if you look at in this, what has happened in the past few decades, you have convolutional neural networks, which play a very, very important role in image and video data processing, recurrent neural networks for sequential data, and also language natural processing and speech processing. And then you have the encoder-decoder framework, which is often used for image or sequence generation. So these are extremely popular models. But nowadays, when you look at large language models, you have transformers, reinforcement learning. These are the methods which there is a lot of focus. And in particular, when you go beyond these into more generative methods. So I've actually listed some topics here, but this is a field, and I invite you just to take a look at it. There's a discussion of Boltzmann machines. You will find a discussion, I'm not going to read, on autoencoders, which we discussed, Bayesian machine learning, which is a hot research field, reinforcement learning. And this is something which is also covered by the some of the more advanced courses, which are listed in the lecture notes. We have transformers, adversarial learning, and much more. And with quantum, there is also quantum machine learning, and quantum reinforcement learning, quantum deep learning, etc. So I would say that with the advent of particular large language models, there is a revolution which has taken place. And I like to say the best way to predict the future is to create it. So all machine learning practitioners, whether scholars, engineers, professors, students, need to work together to advance these important research topics. So it's a field still, when you look at machine learning and artificial intelligence, it's a field where we still can actually get into new hot areas with not much large investments. However, what is going to become more and more important is actually access to high performance computing facilities where you have access to GPUs, etc. So one of the things I recommend is always, and since many of you may actually have data heavy projects for project 3 or data sets, is to get an account on the machine learning nodes which we have at the university. So these, you just search for ML nodes, UIO. I think I've said this many times. And you apply for access, and you can use this for free. And you will get access to not the latest NVIDIA GPU cards, but you will still get access to the GPUs, which will allow you to run, your runs will go much faster, and you will be able to process much more data and analyze bigger models and develop bigger models. So I recommend using the resources we have. We don't know what the future will look like because many of the models become much more data intensive. If you think of the large language models, they're actually being trained on trillions of parameters. And they do also suck a lot of electricity and electrical power. So we haven't discussed much about ethical aspects of machine learning and AI, but the energy consumption is a huge issue. In countries like Ireland, 20% of the national electricity production goes to big data centers. And that's a lot. So this is a little bit about some of the consequences. So we can still do a lot with a simple infrastructure, because many of the algorithms are driven by the ideas which you have. But at a certain point, access to high performance computing facilities become important. And that can be a kind of hinder of further developments. So I hope that we can have this situation where we have a nice mix between algorithm development and also having a pretty reasonable access to high performance computing resources for everybody. Because then the participation, the democratic participation in the development of AI and machine learning methods is hopefully much larger than it could have been if very few people had access to the computing resources. So a little bit about ethical perspectives. I always find it very sad when the semester is over, but I have to wish you the very best. And thanks for coming today towards the end of the semester. And I hope you enjoyed it. I have enjoyed it, as always, to get in touch with you guys. This is my last word. Ciao. Okay, guys. Enjoy your time. So, and don't hesitate to ask. Thanks for coming.